Suppose this is an infinitely thin rod, and recall the center of mass for a discrete body. While treating this rod as a continuous body assembled of these infinitely thin elements, we can take the limit of each sum as n approaches infinity. So we have this rod being assembled with an infinite number of masses. So therefore we obtain the following integral expression. Now if we visualize this as a differential mass element, then that's equal to the density by the volume of the element. And for this one-dimensional rod, we have a uniform area. So effectively, the volume is area by dx. So what we call this is lambda, or the linear density. So for this one-dimensional rod, we can write the center of mass as follows. Where we're integrating over the length of the rod. So if lambda changes with respect to x, we can't take it out of the integral. But if the rod has a constant density, we can take the linear density out of the integrals and cancel them out. Now in contrast, if we consider this rod as two-dimensional with a thickness, so this here is now our differential area element. So in this case, our differential mass element is going to be the density multiplied by the thickness of the rod, which is uniform out of the plane. So thickness multiplied by the differential area is going to give us the volume. So what we call this is sigma, or the areal density. So in this case, for our two-dimensional body, we integrate over the area and replace the linear density with the areal density.